Yeah. Okay, so in denary number system base 10, this is how we add numbers. 5 plus 5 is 10, and if it is 10 or more, we keep the right hand digit and take 1 as the carry forward value to the other side, and then we add it to get the value. In binary, the values that we can have are 0 and 1. So what we do is, when we add, if it is 2 or more, we keep the first digit and take the bit, we carry forward the bit to the other side. So 1 plus 1 is 2. 2 is represented in binary as 1 and 0. And if you're wondering how we get 1 and 0, it's like this. When you convert a denary number to binary, we go on dividing it by 2. 2 into 1 is 2, and in front of that we put the remainder. So 2 into 1 is 2, and the remainder is 0. And then when we write the binary equivalent of 2, we write it from bottom to top. So that's 1, 0. So this is 2 in binary. It's 1, 0. 3 is represented as 1, 1. Now what we do is, when we add these two, 1 plus 1 is 2. In 2 we keep 0 and take 1 bit to the other side. 1 plus 1 is 2. Keep 0, take 1 to the other side. Just like denary addition. 1 plus 1 is 2. And then we keep 0 and 1 there. And this is the answer. To check whether this is the correct answer, we'll convert this binary number to denary and see. Okay, 101. If you convert 101 to denary, check my previous video. We did this. We write the positional values of this bit stream. So this is starting with 1, this is 2, this is 4. All these values are powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, like that. Up to 128 is fine, because we deal with 8 bits in this exam. So we have 1, 4, we have 1, 1, there are no 2's, so the answer is 5. So 101 is denary 5. If you take 1, 1, you already know that 1, 1 is 3. Okay, so if you add 5 and 3, if you add 5 and 3, that's going to give you 8. So this is supposed to be 8. Okay, let's see whether it's 8. 1, 0, 0, 0. How do you convert? You write the positional values in this bit stream. This is 1, 2, 4, 8. Okay, there's only 1 8, so the answer is 8. This is correct. Understand? Is that clear?
Yes, sir.
Okay, great. So let me share the screenshot. You can write these things in your book or your exercise book. Make sure that you update, highlight, and everything. Right, let's look at some example questions, right? Okay, I open this in pen drive. Let me open it separately. Okay, here we go. Right, so we looked at binary addition and denary addition also, right? Let's do these questions. Carry out the following binary additions. Okay, now when you do this, you will notice that now you notice that all these binary numbers are having 8 bits. So this is what I told you, right? In this book, in the exam, when you're adding binary numbers, you deal with only 8-bit binary or 1 byte. When we are adding 8-bit numbers, okay, now see this problem, okay? When you're adding 8-bit numbers, this has caused a problem. All 8 bits have been used, and the one that was carried over in the last column has nowhere to go. Okay. Therefore, the result of the calculation would be wrong. Okay, let's look at an example, then we will understand it clearly, right? Okay, okay, let's take this one, right? Are you guys fixing the cameras and everything? Okay, let's take this example, right? 110. You also take a piece of paper or take your exercise book and do this along with me. 110, 101, 10. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 bits here, right? Okay, we are going to add that to this one. 0, 1, 1. You also do it. 0, 1, 1, 0, 0. If you do it only, you will understand this, right? 1, 1, 1. Okay, we are going to add this. Okay, now you know that we are adding two 8-bit numbers. Let's see what happens. 0, 1, 1. 1 plus 1 is 2. You don't keep 2, right? You know that 2 is 1, 0. 3 is 1, 1. So you keep 0 here and take 1 as a carry bit to the other side. 1 plus 1 plus 1 is 3. That is 1, 1. So you keep 1 there and take the carry bit to the other side, 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 2. So you keep 0 again, take the bit to the other side. 1 plus 1 is 2. So you keep 0 and take the 1 to the other side. What happened? Now the resulting answer has 9 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 9th bit. Okay. Now imagine we have designed a system to work with only 8-bit numbers, only 8 bits, but the register that we have made is only capable of keeping 8 bits. What will happen? Where is it going to keep the 9th bit in this result? There's no place. So what will happen is this last bit will be gone. And the answer is going to be wrong, right? These bits here is not giving the correct answer. We need this bit also. So this error is called overflow. Overflow error. Understand? Did you understand? Feel free to disturb me and give me the feedback. Okay. Did you guys understand what happened actually? What happened here? And if you want me to explain again, let me know. We were adding.
No, sir, understood.
Understood, no? We were adding two 8-bit numbers, and the resulting value had 9 bits. So if we had designed our system to hold only 8 bits, the 9th bit will be lost. When you lose the 9th bit, the result is going to be wrong. This error is called overflow error. An overflow error can be can have drastic effects, right? Serious consequences. Now, if you look at this example they have given here, Now look at this. Overflow error, this condition occurs when a calculation produces a result that is greater than the computer can deal with to store, right? So as an example, you can take, okay, if you are dealing with 8-bit numbers, and if the resulting value has 9 bits, the last bit will be discarded. As a result, the answer is wrong. This is called overflow error. Okay. Now see the consequences, right? Overflow errors have led to many real-life disasters. The most famous was the crash of Ariane 5 space rocket, which exploded in 40 seconds after its launch in 1996. Others include the failure of a Patriot missile defense system in 1991. Do further research to find out more about overflow error. That's crazy, right? Just 1 bit causing this much of a disaster is unbelievable. Okay, so that's called overflow error. Right. So shall we do these questions there? Please. Okay. You also do it. I'll also do it here. You also do it, right? Okay, let's take the first one. A. Do it in your book, okay? Okay, let's do it, right? Have you written? Did you write all this? Are you ready to calculate? Tishan, okay? Where? This Chinese or Korean letters must be Bokum, right? Is that Bokum? Bokum, is that you with these Korean letters? Korean or Chinese? I don't know. Japanese, I don't know. Okay, he went. Oh no, this Tanuti, no? Okay, okay. Right. So let's do this, right? 0 plus 1 is 1. 1 plus 1 is 2. And you can write it somewhere. 2 is 1, 0. 3 is 1, 1. Okay. So if it is 2, you put 0 there and take 1 to the other side. 1 plus 1 is 2. Again, keep 0. Take 1 there. 1 plus 1 is 2. 0, 1. This time 1 plus 1 plus 1, 3. So you keep 1 there. Take the other bit to the other side. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 1, 0. I can see the first one, first addition has an overflow. Overflow. Okay. Is this the answer you got? Can I see a thumbs up if you got the same answer? Okay, great. Next one, B. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. That is, you keep 0, take the 1 to the other side. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. Okay, is that the answer you got? There's no overflow in this. The result is also having bits. Is this correct? You got the same answer? Okay, great, excellent. If anyone wants me to explain again, let me know, right? Okay, the third one, 1 plus 0 is 1, 1 plus 1 is 2, so you keep 0, take 1 to the side, 1 plus 1 is 2, keep 0, take 1 to the side, 1 plus 1 is 2, keep 0, take 1 to the other side, 1 plus 1 is 2, keep 0, take to the other side, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 2, you keep 0 and take 1 to the other side. Okay, there is an overflow here. Is that correct? C? What about C? Is that the answer you got? Okay, great, excellent. Right, let's move to the next one, right? Okay, so now it's going to get a bit more advanced and a little bit difficult, right? Signed and unsigned numbers. Okay, so far we have been considering the whole numbers or integers that are positive. But how can we represent negative numbers in binary? When an integer is indicated as a positive or negative in denary, we put plus or minus like this, right? A symbol. But in binary, we can't do that, right? How can we put plus or minus like this? Even plus and minus are also represented as binary in ASCII code, right? There's an 8-bit binary for plus, for minus as well. So how am I going to represent plus and minus? That's what we are going to talk about here. We cannot do this because we cannot simply add an extra bit. Also, the processor would not understand plus and minus symbols. So one method of representing negative numbers in binary is called sign and magnitude method. Sign and magnitude method. Now, this is something that you learn for every computer science course at the beginning, but not for IT. Okay, not for IT in most of the courses, but usually computer science. In a multiple bit binary number, the leftmost bit, the one with the greatest value, right, that is called the most significant bit. Now, why is it called the most significant bit? Because you know that the positional values increase from right to left, right? How? 1, 2, 4, 8, 16, 32, 64, 128. How many bits are there? 8 bits. 1, 1, 1, 1, 1, 1, 1, 1. 8 bits. So the most significant bit is this one. Is this. Why? This is the bit which has the highest positional value. Okay, so this is called the most significant bit. In maths, you must have heard about something called most significant digit. This is most significant bit. And the least significant bit is this. This is the one which has the lowest positional value, LSB, and this is MSB. Okay, first you understand that. We can use this to represent the signed integers. Right? Signed integers. What does that mean? If you take the most significant bit, right, you know a bit can be either 1 or 0. If you use this bit, this most significant bit in an 8-bit binary number, and if we can use this to represent whether the number is a positive value or a negative value, we have sign and magnitude method. How do you do that? If it is 1, we represent a negative number. That is, if the most significant bit is 1, we are representing a negative number. If the most significant bit is 0, we are representing a positive number. Simple as that. So remember, 1 is negative, 0 is positive. Understand? Is that clear? Anyone who's not clear? One is negative, 0 is positive. Tanuti, what does that mean? You didn't understand, or you understood?
I didn't understand, sir.
You didn't understand. Okay, right. So do you understand most significant bit?
Yes, sir.
That is the bit which has the highest positional value. So it goes like this: 1, 2, 4, 8, 16, 32, 64, 128. In the last class, I told you how we get these numbers, right? Because they have positional values. Just like if you take a denary number like, let's say, denary number like 858, right? These are ones, these are tens, these are hundreds. And how do you get them? This is 10 to the power 0. This is 10 to the power 1. And this is 10 to the power 2. Please make sure that when you come to the class, you go through the previous video if you missed it, right? Similarly, if you take a binary number like this will be 2 to the power 0. This is 2 to the power 1. This is 2 to the power 2. 2 to the power 1, sorry, 2 to the power 0 is always 1. Any numbers, 0th power is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. That's how we got these numbers. 1, 2, 4. It goes as powers of 2. So simply multiply this number by 2 to get the next number. 1, 2, 4, 8, 16, 32, 64, 128. Why do we stop at 128? Because we are dealing with 8-bit numbers. Now, in sign and magnitude, what they're going to do is they're going to reserve the most significant bit to represent whether this number is positive or negative. If the most significant bit is 1, we are representing a negative number. If the most significant bit is 0, we are representing a positive number. Simple. Therefore, using this method, binary this, okay, 0, 0, 0, 1, 1, 1, 0, 0. You can see the most significant bit is 0. So this is going to be a positive number. If this is if the most significant bit is representing the positive or negative, we call that the sign. We call it the sign. So what is the sign? Whether it is positive or negative. So this is called the sign. You can call it the sign bit also. So the most significant bit is representing the sign, and that sign here is plus. Then what do you call the rest of the bits? The rest of the bits are called magnitude. Magnitude. I think that now it's clear, right? Tanuti, is it clear now?
Yes, sir.
So we have the sign and magnitude method. So it's only the magnitude that will represent the number, right? In this, you see a problem, right? Already you see a problem. Why? You're losing one bit. That bit was used to represent the value, but you can't use it because now it's representing the sign. So you have only 7 bits to represent your number. So there can be limitations like that. Okay, now take a look at this number. It is a positive number because the sign bit is 0. And what does it represent? Okay, they say it's 28. Let's see whether it's 28. How do you convert this binary number to denary? Write the positional values. 1, 2, 4, 8, 16, 32, 64. This is taken, so we can't use it for the magnitude. Okay, now how do you calculate what this number is? We just add the positional values if there are ones. So we just multiply the bit by the positional value and then we add them together. So 0 into 64, nothing. 0 into 32, nothing. Leave it out. That's 116 plus 18 plus 14. No 2s, no 1s. So the total is 28. That's how we get it. And ultimately, this is representing plus 28. How do you know it's plus 28? Because the most significant bit is 0. Simple, right? Okay. Now, when you get used to these calculations, you do it mentally, right? You don't need to write like this, right? 16 plus 8, 24 plus 4 is 28. Okay, then what about this one? You can see the most significant bit here in the second one. It's 1 0 0 1 1 1 0 0. 1 2 3 4 5 6 7 8. First you check whether there are 8 bits. All right, so the most significant bit is 1, which means this is a negative number. Okay, then what is the magnitude? Magnitude is same as before, so you know that it's going to be 28, but this time it's minus 28. Simple. Is that clear, everyone? Is that clear? Any questions? Anyone wants me to explain again? That's how you represent negative numbers in binary using sign and magnitude. Sign and magnitude method. Is that clear?
Yes, sir.
Okay, great. Then let me give you a question. Okay, can you guys convert this into? Okay, can you represent this? Represent minus 56 using 8-bit sign and magnitude method. Okay, I'll give you 5 minutes. What do you have to do? First, you need to represent 56 in 8-bit binary. Okay, 8-bit binary, you have to represent 56 in 8-bit binary. And you know how to convert denary numbers to binary. We did that in the last class. So make sure that you watch the videos. So get the binary equivalent. And if there aren't enough binary numbers, make sure that you add some leading zeros to make it 8-bit. And after that, you take the most significant bit and represent this negative sign using 1. That's all. Okay, I'll give you 5 minutes. Can you quickly do it? Right, so first we need to represent the 56 in 8-bit binary. And that day I showed you an easy method to do this, which is also in the book, right? So what we do is this. We write the positional values for 8 bits. 1, 2, 4, 8, 16, 32, 64, 128. The normal method would be to divide 56 by 2 and go on dividing until it is not further divisible by 2, right? The easy method is this, but depending on the question, you need to use either method 1 or method 2. Now, tell me 56. You have to put 56 into these slots. Do we have 128 in 56? Do you have 128 in 56? Yes or no? Do we have 128 in 56?
No, sir.
No, right. So we put 0. Good. 64s? No 64s? 0. 32? Yes.
Yes.
We have 132. Can you put 2? Anyway, you can't put 2 because it's 56, right? If it is 2, it will be 64. So you can't put 2. 132 is fine. So 56 minus 32, that will be 424, right? 24. So in 24, do we have 16s? Yes, 16. So 24 minus 16, we have 8, right? 8. In 8, we have 1 8. Okay, so 8 minus 8, 0, everything gone. And now we have no zeros, sorry, no 4s, no 2s, and no 1s. Is that what you got for 56? Is that correct?
Yes, sir.
Okay, now you can check like this also, right? That's 132, 116, 32 plus 16 is 48, plus 8 is 56. Okay, we have got it. 32 plus 16, 48 plus 8 is 56. Okay, now let's write it down. 0, 0, 1, 1, 1, 0, 0, 0. Okay, now we are trying to represent minus 56. Now this is 56. Okay, if it is, we can even call this plus 56 because you can see the most significant value or the bit is 0, and you know 0 represents positive. So this is positive 56. If it is minus or negative 56, this bit will be turned to 1. It's so easy. The rest will be the same. 0, 1, 1, 1, 0, 0, 0. This is the answer. Easy, right? All of you got it?
Yes, sir.
Okay. Okay, I'll take 5 minutes of your time. The next one we are going to learn is called 2's complement method. Now this one is a bit difficult. Little bit more difficult than the previous one. So this is the second method we use to represent negative numbers. The most common method, and this is the most common method, okay, used to represent signed integers in modern computers is 2's complement method. Right? It's really easy. I mean, at the beginning it will be a bit confusing, but really easy. This method of representing binary numbers to show whether they are positive or negative. This method works on the principle above. The result of any number added to its negative equivalent should be 0. Okay. So, all right, let's look at this one, right? Okay. It involves the 3 steps. 3 steps. What are the 3 steps? First, first step is to represent the number in 8-bit binary. Okay. Represent the number in 8-bit binary. You can write this in your book, okay, in this section. Eight-bit binary. Represent the number in 8-bit binary. That's what we have done here. Okay, let's find out what this number is, what this binary number that we have represented here. So you write the positional values 1, 2, 4, 8, 16, 32, 64, 120. Feel free to tell me if you don't understand. Okay, 1, 2, 4, 8, 16, 32, 64, 120. That is because we have 8 bits. Okay, what is this number? Can anyone tell me what this number is? What is this binary number represented here?
28.
28, good, excellent. it's 28. How do you get 28? 16, that's 116, 18, that's 24, that's 14, that's 28. 16 plus 8 plus 4, 28. So first you write the binary equivalent of 28 in 8 bits. In 8 bits. Okay, what is step 2? Step 2 is flip the bits or invert, right? Invert the bits. Invert or flip the bits. What does that mean? If it is 0, make it 1. If it is 0, make it 1. If it is 1, make it 0. Simple. Right? 1, 0. 1 to 0. 0 to 1. 0 to 1. 0 to 1. Just flip the bits. That's all. The last step is add 1 to the flipped bits. That means you have to add 1 to this flipped bits. Okay. That's not this one. This is the answer. You have to add 1 to this one. Where shall I write it? Right. This is step. Second step. And this is step 3. Okay. So let's do it. We have 1, 1, 1. Right. I'm writing the flipped bits. 3 zeros. 2 ones. We have to add 1 to this. 1 plus 1. Now you know binary addition. 1 plus 1 is 2. So you write 0 there. Take 1. 1 plus 1 is 2. Keep 0. Take 1 there. 1 plus 0 is 1. 0 here. 0 here. 1 here. 1 here. 1 here. There you go. That's the answer. 1, 1, 1, 0, 0, 1, 0, 0. So easy, right? Understood? Is that clear? What is the first step? You write the binary equivalent of the denary number in 8 bits, right? If you don't have 8 bits, just put leading zeros to make it 8 bits, right? Let's say your number is something like this, 1, 0, 1, 1, like that. So you have only 4 bits, right? So what you do is you fill 8 bits to the left side, okay? Not to the right side, right? So 1, 2, 3, 4, 5, 6, 7, 8. Now we have 8 bits. After completing 8 bits only, you go to the step 2. That is inverting the bits. Inverting means, or flipping the bits means, you make 0, 1, you make 1, 0. Do you know that once you flip the bits, that is called ones complement. Right? When you flip the bits, that is called, the result is called ones complement form. Ones complement. So in order to make 2's complement, what you do is you add 1 to the 1's complement. This is 1's complement. You add 1 to that. And the result is 2's complement. Get it? 2's complement. Result is 2's complement. Okay, so what are the steps? Represent the denary number in binary, 8 bits. Okay. Flip the bits to convert into 1's complement. Add 1 to convert it into 2's complement. Understood? Is that clear? All of you?
Yes, sir.
Right. So that's one of the most important calculations in this binary chapter, right? Most of the time you get this. Right. You don't need to go through these. If you go through these, it'll be confusing. Just follow what I showed you. And let me give you a homework. Okay, here we go. If you send me the homework, I will be able to correct and give it back to you, right? So make sure that you do it. Take a photo, do it on your book, take a photo and send it to me, then I will correct and give it. So you do only these, this one, and this one. These three, right? This one I will teach you in the next class. If you can give a try on this. Showing your working, carry out the binary addition of 90 plus minus 33. So here what we're actually doing is, now why did they put plus and minus in brackets? Because what you are actually doing is you are adding the 2's complement of minus 33 to plus 90. That's what you're actually doing here. You are adding 90 and the 2's complement of minus 33. Right? It's so easy. All you got to do is just represent 90 in bits, 8 bits, right? And show minus 33 in 2's complement, 8 bit. And then add the 2. Just add these 2. So give it a try. I will explain that in the next class. But these 3, of course, you can do today itself. Okay. Right, then see you tomorrow. But I'll be having extra classes throughout, right? Because we need to finish this and we need to do papers. This is going to be your first paper. So you need a lot of practice. And we have like almost 1 week only. If Colombo does some changes, I will let you know. If they are like omitting certain sections, I will let you know, because they are the ones who are making the paper. They are also finding it hard to finish everything. Let's see how it goes. But your job is to revise and study what we have done so far. Okay, see you then. Have a nice day.
Thank you, sir. Have a nice day, sir.
Okay.
Thank you so much, sir.
Okay, see you. Bye.